presented by Caltech.
So in talking about interference of waves, I have a little demonstration here that is kind of nice. In terms of water waves instead of some of the other things we've been talking about. So I just have a pond with water in it, and I can excite waves. So you can see on at least one screen so there's two probes that are going up and down making waves, and they're going fairly slowly now. Go a little. So you see, it may be a little hard to tell with that, but the wavelengths, as you get out a ways, are rather large. See a little better that way. And hopefully you can start to see a little bit of the interference. It'll be easier to see if we raise the frequency some. So you can see these lines, I don't know, it's maybe right around there is a line of nodes. In between you get the antinodes. As I increase the frequency, I'm getting more and more of these. So now I've got a line of nodes there, and another one there, rather closely spaced. And now I can get pretty much twice as many. A nice pattern. You see how the wavelength, if you're far enough from the source, decreases as you go up in frequency, and how the angular separation decreases as well between the nodes. So that's in water, what we've seen in other contexts before. So we were talking about the Young double slit experiment and the single slit and the diffraction patterns from those. Those have the characteristic that we examined, we did the analysis in the context of, a little more light, in the context of being far away from the aperture, known as Fraunhofer diffraction. If we violate that and go closer, we can get different effects. So I'm going to discuss it very briefly, but I want to show you a case where we're actually close to the observation point. So we're at the observation point over here with this screen. Our object is over here. It may not look like that's very close, but we'll calculate it based on the criteria that we have. So turn this on. You see something there? You don't see anything there. Okay. Curious. Well, you're going to have to look on one side. So what I've got is a laser going through an aperture, but then I've got a little ball here. Ball that's half a centimeter to a centimeter thick. I'll let you see it a little better there. It's a little ball there. It's a little tiny ball. And so I'm letting the light come in and diffract off of that ball. So it's maybe not quite the same situation as the others. It's not a slit or a double slit, but we can still get diffraction from it. Oh, I know what the room. Now I got it. Okay. So it's a little hard to see, but you can see there's a bright ring around the outside where most of the light's going, but you can see that there's also a little dot in the center, which I may be able to just adjust the collimator here and change, but it's always there. I mean, it's coming from the ball. It's not coming from my collimator here. So we can diffract from a lot of things. Almost, I mean, any object you put in the way of a light beam is a potential source of diffraction. But the characteristic of this is that I am in what's called the near field, more or less. And I'd like to say a little bit about that. When we turn the lights back on. But let me, just, since I've got the lights off, let me do a couple of other things here. So the next topic after we've finished with this diffraction is going to be dispersion. And dispersion is what happens when your relation between omega and k, when your velocity depends on actual frequency. So with these monochromatic sources, it's just one source, so we're not seeing any effect of whether there's some velocity-dependent speed going on. But we can see other things that do show this. So over here, I have a diffraction grating, which is basically just a lot of slits. So it's a whole bunch of slits. So we take the Young double slit and go to an extreme of many slits. And there's a collimator here that is just a slit over the projector. And so you can see you get the bright light there at the center. That's just this center slit. So that's the 0 degree angle. So we know from our single slit that we get an image, a bright image at the center at 0 degrees. And the other things are separated in a wavelength dependent way. The fringes away the sides are wavelength dependent, but that center image is not wavelength dependent. All wavelengths will have a center image that's at 0 degrees, and so all wavelengths are contributing to that center image. So that's why there's no color in that center image. But then if you go to the side, the first fringe at the side, and you can see at the other side over there, the first fringe at the side, what do you know? The colors are separated. So this is an indication of the fact that that we calculated that the angle to the first fringe is a function of a wavelength. Remember, we had this lambda over a dependence as the angle. So we looked at the size of the slit. We changed a, so we could change the distance and angle there. But now we're changing the wavelength. We're shining many wavelengths all at once on this, And we're seeing that as you get over, as you look at lambda over A, lambda's changing. Fortunately, red is a longer wavelength than blue, so it's going in the right direction. And so now that we have many wavelengths, we actually see the dependence on wavelength. So when we have a refractive medium, the index of refraction can be a function of wavelength as well. And so all I have here is a white light from a flashlight that's shining through a slit, a collimator. It's wide open, so I don't care. There's not too much diffraction going on. And it's going through a prism here. And so the prism, the light's going to refract in there, but because of dispersion, it's going to refract a different amount for different wavelengths. And so it's taking the white light and spreading it out into different wavelengths. And so that's what we're going to talk about next is this dispersion phenomenon. Okay. Any questions on these? I want to talk about this guy a little bit more. So we've talked about, I've forgotten where that is. Maybe I'll find it, maybe I won't. I will find it. So we've been talking about diffraction in the sense of Fraunhofer diffraction. Which is otherwise known as far field. Our observation is far from the object that we're diffracting from. So we used that approximation when we did the analysis. We assumed that the distance to the observation point was long compared to the size of the aperture. If we relax that assumption and go closer, we get what's called Fresnel diffraction. So Fresnel diffraction is also an approximation on the exact case, but it's not as great an approximation as the Fraunhofer diffraction, and we can get a different dependence. So instead of, say, a linear dependence of the phase, depending on the position of the aperture, we could actually get a quadratic dependence. And so our patterns can be different. And so you could still get patterns that look like this, where, say, you get rings of light or dark. In the Fraunhofer diffraction, this center spot is always bright. But in the Fresnel diffraction, this center spot can be either dark or bright. We diffracted off an object there, and we got a bright spot, but that's not always the case. Okay. So To decide which regime you're in, there's a kind of a rule of thumb known as the Fresnel number. So you know, the less approximations you make, the more difficult the calculation becomes. So I'm not actually going to go through a calculation because they do get rather difficult. A Fraunhofer approximation is a nice calculable approximation. The Fresnel number is defined as the characteristic size of whatever you're diffracting from divided by the distance to the operation point times the wavelength. So A equals object size L equals distance to observation, and lambda is the wavelength. So we can make an estimate for the Fresnel number for that. And the point is that if this number is less than or order 1, we're in the far zone. L is big. So in that case, we're doing Fraunhofer diffraction. And if we're 1, if we're bigger than 1, we're in what we might call the near zone. Fresnel diffraction. So it's just our geometric approximation of the Fraunhofer case breaks down, and so you have to do a more careful calculation. So what do we have for that? So let me just roughly say that A is, let me just call it half a centimeter. It's actually a little bit bigger, but that'll make it even bigger up here. So A is about 5 times 10 to the minus third meters, 5 millimeters, roughly. Lambda, well, okay, I used 5 times 10 to the minus 7 meters. So I used 500 nanometers. It's probably a bit longer than that. So it was red light that I was using, so that's maybe a little short, but it's going to be close enough. And L, what is that, 3 meters? I used 5 meters. Let me use 5 meters. Okay. So I'm overdoing the distance. But that's just going to make the number smaller. And I just want to show that it's fairly big. A squared over L lambda. With these numbers, I mean, we did have 5 meters when I tried it out yesterday, and the same effect was showing. So they're not different. Okay, 25 times 10 to the minus 6 is A squared, meter squared. In the bottom we have, now you see why I chose what I did. 25 times 10 to the minus 7. Okay, the 25s cancel, and we get this as approximately 10. That's a number bigger than 1, so we're in the near zone. And if you remember when we did the single and double slits over here and projected up on the wall, well, that's a long ways away, but my slits were really small. And it goes like A squared. So they were much smaller than that. You know, it's fractions of a millimeter. And so, so the Fraunhofer diffraction for those slits that I showed up on the screen was the relevant calculation. So that's really all I wanted to say about Fresnel diffraction, is just to mention that it exists. It's just a different regime in doing the calculation. And you know, if you have a regime like that, it just becomes a more complicated calculation. And the effects can be somewhat different. Okay, so that's all I want to say about that, just to let you know that it exists. I want to go on to dispersion. So this is our last big topic, but it's a very important one. We have dispersion of waves all around us. We've seen the example of dispersion in the prism. So the velocity of a wave could depend on frequency. And that introduces dispersion. If a wave has multiple frequency components, then depending on what we do with that wave, we can have the different frequency components do different things, follow different paths, or take different amounts of time. Okay. So let's consider first, what we'll call a wave packet. We'll make it a simple one and get a little more complicated as we go along, or more general. So let's consider a wave packet consisting of just two frequencies. And let's suppose it's the same propagation speed, so to start with. So we have one wave that's in our packet that we'll write as amplitude A times cosine K1x minus omega 1t, and psi 2 is A cosine K2x minus omega 2t. And I'm going to assume now that they have a common velocity, v equals omega 1 over k1 equal to omega 2 over k2. So there's no dispersion going to happen with this, okay? Just starting simple to see what happens. And I've given them both the same amplitude for simplicity as well. So now I take the superposition. So I make my wave packet by adding them together. Okay. So that's easy. Everything's linear. They just add. So I'll get an overall wave, which is the sum of these two, which is just A times cosine K1x minus omega 1t plus cosine K2x minus omega 2t. Let me write this in a little bit more interesting way. Especially interesting if omega 1 and omega 2 are about the same. So we'll use the identity that says that cosine of alpha plus beta plus the cosine of alpha minus beta is given by 2 cosine alpha cosine beta. It's just a trig identity. And so then we can write psi is equal to 2a. So you can see it's of this form in the sense that we've got, the minus sign or plus sign. It's just in the sign of whatever you're using, sign of beta there. But so if we use that identity, we can write this as k1 plus k2 over 2 times x minus omega 1 plus omega 2 divided by 2 times t times cosine of k2 minus k1 over 2 times x minus omega 2 minus omega 1 divided by 2 times t. So that's what the trig identity gives me. So let's consider a given x and look at the time dependence. And for simplicity, let's just take x equal to 0 so I don't have to write a bunch of stuff. But I could consider other positions too and have the same features coming out. So psi at x equals 0 is just 2a times the cosine of omega 1 plus omega 2 over 2 times t times cosine of omega 2 minus omega 1 divided by 2 times t. And now let's suppose, so that's, I haven't made any approximations there, but now let's suppose, for the sake of thinking about this, let's suppose that omega 1 and omega 2 are both about omega. Yeah. Yeah, but the cosine's symmetric on it, so I just dropped it. Yeah, sorry, I threw that by you. Then, okay, then we can write this as then psi of t is approximately, for x equals 0, is approximately a of t cosine omega t. So I pick some point and I call it x equals 0 and I look at what the wave does. Where I've separated out into this a of t the other cosine. So a of t is, well, it's the 2a times the cosine of omega 2 minus omega 1 over 2 times t. So the idea is that I've got some overall sort of high frequency cosine omega t here, and then I've got something that's going at a frequency of the difference between the two, which is small. So I'm modulating this cosine omega t with something that has frequency omega 2 minus omega 1 over 2. And so that's, so we're effectively modulating our wave. Our wave of frequency omega, which we could think of as a carrier wave, if you're thinking of radios or something. With the modulation of the beat frequency. In this case, omega 2 minus omega 1 over 2. And so what's going on is we have our beat frequency here that's modulating a high frequency wave. And we did this before when we had two signal generators set up over here. We tuned them to 1 hertz apart, and you could hear the beats in the 1 kilohertz signal. And of course, as you know, this idea of modulating some carrier wave is what we do in AM radio, amplitude modulation radio. So we're just modulating the amplitude of our carrier wave, of the high frequency wave. So this high frequency wave might be a megahertz if you're in the AM band, and then the low frequency range may be a kilohertz if you're talking, or 500 hertz, or whatever you talk at. So let me call the carrier frequency call that a carrier frequency. Omega sub c for omega carrier. When we do AM radio in particular, we modulate at audio frequencies. So F sub c maybe a megahertz. You know, anywhere from 890 up to 1600 or whatever. We modulate this at audio frequencies, and we get psi is equal to A plus sum over frequencies, call it over index m, of some amplitude B sub m, e to the I, omega sub mt, times sine omega ct. I could have written cosine omega ct too. It's just a wave. Okay. So this would be our modulation of our carrier frequency, where these are audio frequencies, and this is the AM frequency of a megahertz or so. So that suggests that in order to make this work, see, we're getting sums and differences of frequencies here. And so if we're modulating our carrier wave, we're actually giving it other frequencies. Because in the superposition, when we add and subtract these, we get other frequencies. Omega 1 and omega 2 aren't exactly omega c. They're getting modified by the fact that we're modulating with audio frequencies. And so that says that we better not have radio stations too close to each other. We're going to get sum and difference frequencies between omega m and omega c in our wave packet that we're actually getting. So we get omega c plus or minus omega m components in our radio wave. And so if somebody has a carrier wave of a megahertz and somebody has a carrier wave of a megahertz plus 1 hertz, they're going to overlap because omega m is much bigger than a hertz. And so the bandwidth or the range of frequencies that you need in AM radio is of order 20 kilohertz. So if your normal audio range is 10 kilohertz, say, you need that on either side of the carrier frequency, so you need a bandwidth of order 20 kilohertz. And the US regulations are that stations can't be any closer together in frequency, in their carrier frequency, than 10 kilohertz. Which kind of maybe interferes a little bit for high-pitched voices. All right, okay, so all of this is, all the frequencies are propagated with the same velocity here. So let's think a little bit more about that. So instead of this, independent of frequency, let's suppose that it's no longer a fixed proportionality. So V may be different for different frequencies. And so the relation between omega and K, I mean, here's a relation between omega and K, but there could be other relations that we'll be considering now. This relation is called the dispersion relation. Dispersion relation. And so then the question is, well, what happens to our superposed waves? So what happens to these waves? Well, let's see. So we just go through it again. Psi 1 equals, we're still giving amplitude A, cosine K1x minus omega 1t, and psi 2 equals A cosine K2x minus omega 2t, or psi equals psi 1 plus psi 2 equals 2a times cosine K2. So all of this just carries over because we didn't, when we did it before, we just did it in general. So that's the same. But now we have possibly different velocities. V1 and V2. Okay, so I'd like to pursue this a little bit and see what useful we can get out of this, okay? So I'm going to so again, I'm going to take the, omega 1 and omega 2, the idea at least that omega 1 and omega 2 are fairly close together. And so I'm also going to assume that I can write that maybe K1 and K2 are reasonably close together. So I'm going to define K0 at omega 0. As the average wave number and average frequency. And I'm going to let the differences, I'm going to call the differences something simpler. Delta K, I'm going to call K2 minus K1 over 2, and delta omega, I'm going to define as omega 2 minus omega 1 over 2. And so then I can write that psi is just something out front of cosine K0x minus omega 0 t. So again, I'm doing the same kind of thing I did there, except now I have to be a little careful because the velocities aren't necessarily the same with k of x and t is equal to 2a. So it's really just the same thing of x delta k minus t delta omega. So let me now consider some velocities that I can form. Let's define a velocity, we'll call it v sub p. Let's take that to be defined as omega naught over k0. That's the velocity of this wave here. Okay? I mean, this is a wave that's propagating with speed v sub p. I mean, if you like to think about it a little bit in terms of our k1, k2, omega 1, omega 2, we could express it in terms of either one. If I express it in terms of wave numbers, this is just a weighted average of our two velocities, where the weighting is by the wave number. And so the cosine, this part is a wave propagating at speed v sub p. Likewise, I can ask, this is also looks like a wave that's propagating at some velocity, so let me figure out what that velocity is. So likewise, cosine x delta k minus t delta omega corresponds to a wave propagating at the speed of v sub g is just equal to delta omega divided by delta k. So they're not the same speeds. So this, if you like, this modulation term is propagating at a different speed than what we might call the carrier wave. So in general, I mean, if the velocity, if the relation is, as we did earlier, is independent of frequency, then they're the same speed, but they don't have to be, and so they're not necessarily the same speed. If I insert, so the dispersion relation here would be, if I write it down here, omega equals omega as a function of k, say. That's my dispersion relation. If I insert the dispersion relation, this is omega of k2 minus omega of k1 divided by k2 minus k1 in terms of what we call the dispersion relation. So, I mean, we haven't made any approximations that omega 1 is equal to omega 2, but that's where this is most useful to think about. So that's kind of the underlying thing that we'll think about here. And if that's true, if omega 1 and omega 2 are about the same, then it's useful to make a Taylor series expansion of our dispersion relation and see what we get. Or K1 is about K2. Make a Taylor series expansion of the dispersion relation and only keep the lowest terms. So omega of K0 plus or minus delta K. Say, so those are the two frequencies that we started with. Is equal to, so we'll expand about K equals K0. And then we get plus or minus delta K times d omega by dk evaluated at K equal to K0 and higher order terms, plus order delta K squared. And so if delta K is small, then we can just keep the first couple of terms and have a good approximation. Let's see, I need to do some erasing now. So what do we get? So in particular, from this Taylor series, we get V sub G, which we defined as delta W omega over delta K, in the limit of small delta K. This just becomes d omega by dk evaluated at K equals K0. So given a dispersion relation, we can calculate V sub G by just taking this derivative. This is known as the group velocity. It's the speed at which our modulation is propagating in terms of our present discussion. And V sub P is just omega over K. And in the context of our discussion here, that's the speed of the carrier wave. It's known as the phase velocity. The speed at which a given point on the phase of our carrier wave is propagating along. So our carrier, if we make our carrier wave look like this, you know, if we pick a crest on the wavefront, that's moving along at V phase. If we take our modulation, which is superimposed on some carrier, the speed at which, say, the antinode of this modulation is propagating is V sub G. And both of these velocities are obtained from the dispersion relation. So once you have the dispersion relation, you know what both of these are. So let's see. Let's try a dispersion relation. For light in a vacuum, omega of k is just the speed of light times k, independent of frequency. Electromagnetic waves in a vacuum all propagate at the same velocity, known as the speed of light. But we can calculate what our phase velocity is. So this is just omega of k divided by k. Well, okay, that's just c. So that's our phase velocity. And we can calculate our group velocity. That's d omega of k by dk, evaluated at k0, but that's anywhere we want here. And that's just c as well. Take the derivative of that with respect to k, and you just get c. So for light in a vacuum, the phase velocity and the group velocity are in fact exactly the same. You compare this with your Schrodinger equation problem that you did a while back. There you had omega of k is k squared over 2m. Well, okay, h bar squared. I don't know where to put h bar since I always use 1, but it's something like that, h bar squared, k squared over 2m. And so v phase is just omega over k, which is just, oh gosh, do I have to put these h bars in? Something like that, h bar squared, k over 2m. Gosh, how's that going to turn out? Let's see. H bar k equals p. That's the de Broglie relation, basically, in quantum mechanics. It's equal to mv if it's non-relativistic. So, okay, so this is somehow h bar k, so h bar squared. I don't know what to do with the other h bar. H bar times p over 2m equals h bar v over 2. I've probably forgotten some h bars. H bar is always a 1 for me, so I never know how to put it in. But basically, you get v phase is v over 2. I'll figure it out. It's just because it's h bar omega is this. Now I've got it. So I got an energy equaling an energy now, so I got the units right. Okay, so I get to divide out one of these h bars. And I get v over 2.